Hey, what's up everybody? We are going to do a quick video on the cardiovascular measurements lab. So in this lab, you're going to take some measurements. You're going to measure the heart rate of a volunteer. You're going to measure their systolic blood pressure and their diastolic blood pressure. And then you're going to you're going to do some math, figure out their pulse pressure and mean blood pressure. Then you're going to estimate stroke volume and cardiac output. And you're going to do all this stuff before and after doing some exercise, and you're going to see how things end up changing. So that is the plan. Now for heart rate, of course, you can use a stethoscope. You can position the stethoscope to listen to that heartbeat. And obviously, you can count how many times you hear that heartbeat, and you can come up with an answer of beats per minute. So you can figure out your heart rate in beats per minute. And of course, do recall that if you are going to listen to the heart, then you are going to hear two sounds for every single heartbeat. The first heart sound, the lub sound, is due to the closure of the tricuspid and the bicuspid valves. The second heart sound, the dub sound, is due to the closure of the pulmonary and aortic semilunar valves. Okay, now do we actually need to use a stethoscope and listen to the heart itself to figure out heart rate? No, we don't. Without a stethoscope, we can simply take the person's pulse. So right here, this person is taking the radial pulse in that lateral wrist. And if you just count the pulses in a minute, that'll be the pulse rate. And whatever the pulse rate is, it's going to be the exact same as the heart rate. So pulse rate will give you heart rate. Now bear in mind, it does not matter where you take the pulse. You could take the radial pulse, you could take the brachial pulse, carotid, facial, temporal, femoral, popliteal, posterior tibial, dorsalis pedal. Whichever pulse you take, you should get the same answer. Now, once you've got the person's heart rate, the next thing you're going to do is you're going to measure their blood pressure. In this picture over here, we've got the brachial artery running down the arm. We're putting the cuff of the sphygmomanometer around the brachial artery. We're going to inflate that cuff with air, making sure the valve is properly positioned. We got to inflate the cuff pressure so that the cuff pressure is greater than systolic blood pressure. So when you're inflating it, you got to make sure that cuff pressure exceeds systolic blood pressure. Now you can be sure that you've done this properly, because when this situation has occurred, the brachial artery here will totally be squeezed shut. Notice there's no more blood going through the ulnar and the radial artery. So the radial pulse will actually disappear once you've done that. Now, once you've done this, you're going to release the pressure in the cuff by slowly turning that little valve right there. And as you release the pressure, you're going to have the bell of the stethoscope positioned on the antecubital fossa. Going to have it in your ears. And when cuff pressure is between, let's put diastolic over here, actually between diastolic and systolic, when cuff pressure is in between those two, you are going to hear sounds. Now you're going to hear sounds because the artery is kind of occluded, it's kind of squeezed. That causes the blood to bounce around. That makes sounds. When you first hear the sound, so when the sound's up here, when the sound appears, you're going to look at the gauge and you're going to note the pressure, and that is going to be your systolic blood pressure. That, of course, is the high value. It's called systolic because it is due to ventricular systole. It is due to ventricular contraction. Now, when the sounds disappear, when the sound is no longer there, it'll get fainter and fainter, then it'll disappear. But when there's the disappearance of the sound, that is your diastolic blood pressure. So you look at the gauge when the sounds disappear, that's your diastolic blood pressure. That is your lowest blood pressure. It occurs during ventricular diastole. So that is pretty much it. That's the simplified version of taking a blood pressure. Put the cuff on the arm, pump it up, greater than systolic. You'll know you've done that when the pulse disappears. Release the pressure. When you hear a sound, note the pressure. That's your systolic. When the sound disappears, note the pressure. That's your diastolic. All right. On that note, let's keep going just really quick. When the brachial artery is squeezed, so that's when the cuff pressure is between diastolic and systolic, the blood flow is turbulent, and turbulent flow makes noise. When the blood vessel is not squeezed, it's called laminar flow. It's like nice and smooth and you don't hear any sounds. All right, once we've figured out blood pressure, and we got the high value, which is systolic, and the low value, which is diastolic, we can figure out something called pulse pressure. Pulse pressure is how strong the pulse is. Pulse pressure is your systolic blood pressure minus your diastolic blood pressure. So in this case, the high value, the systolic, is 120. The low value, the diastolic, is 80. 120 minus 80 would give me an answer of 40. And my units for pressure are millimeters of mercury. So pretty easy to calculate pulse pressure. Just take the systolic and from it subtract the diastolic. And this is a measurement of the strength of the pulse. And we're going to utilize this measurement in a moment. The next thing I can do is I can figure out something called the mean blood pressure. Mean blood pressure is a weighted average. So mean blood pressure is a weighted average. What we do is we take 2/3 of the diastolic blood pressure and add 1/3 of the systolic blood pressure. So you can tell from this equation that the diastolic pressure is weighted more heavily because you spend more time in diastole. Now, an alternative equation you can use, which will give you the same answer, mean blood pressure equals diastolic plus 1/3 of pulse pressure. So for example, let's suppose somebody's blood pressure was kind of high. Their blood pressure is 150 over 90. That means systolic is 150, diastolic is 90. Now, it doesn't matter which of these two equations we use. We could use the first equation, and we could take 2/3 of 90. Well, 2/3 of 90 is 60, and 1/3 of 150, 1/3 of the systolic would be 50, and 60 plus 50 would give me 110. And of course, this is a pressure, so my units are millimeters of mercury. Now, if I wanted to, I could simply use this bottom equation. My diastolic pressure was 90, and then the pulse pressure would be 150 minus 90, which is 60. 1/3 of 60, of course, is 20. And 90 plus 20 gives me 110 millimeters of mercury again. So pretty straightforward, pretty easy math. Doesn't matter which equation you use. And this mean blood pressure gives me an idea of the pressure that's driving blood flow. Okay, so I've calculated heart rate, I've calculated systolic and diastolic blood pressure, or I've measured rather heart rate, systolic and diastolic blood pressure. Then I calculated pulse pressure, and I calculated mean blood pressure. And now what I can do, because I have pulse pressure, if I actually multiply pulse pressure by 2, that'll give me an estimate of stroke volume. So if somebody's blood pressure is 110, there we go, 110, that's a horrible zero, 110 over 70, well, their pulse pressure in this case is what? It's 110 minus 70, that's 40. 40 times 2 will estimate the stroke volume. The stroke volume would in this case be 80. 80 what? 80 milliliters per beat. And this stroke volume is the amount, the volume of blood ejected by a ventricle per beat. And of course, the two ventricles are going to average the same stroke volumes. All right, once I've estimated stroke volume, and I already measured heart rate, then I can estimate cardiac output by multiplying stroke volume times heart rate. So, for example, if our stroke volume was, 80 milliliters per beat, and the heart rate was 60, that's a 60 beats per minute. Notice that the beats is going to cancel out here. And 80 times 60, you can use your calculator if you need to. Maybe you don't, because 6 times 8 is 48. Add the 2 zeros, and I get 4,800 milliliters per minute. Now, if I wanted to, I could then divide that by 1,000, and that would end up being 4.8 liters per minute. And that is my estimate of my cardiac output, which is the volume of blood pumped by one ventricle in 1 minute. Okay, fantastic. So that's all the measuring and figuring and estimating that we're going to do. And we're going to do this both before and after getting some exercise. And we want to see how things change. And heart rate, of course, as a result of exercise, heart rate is going to go up. The heart is going to be beating faster and stronger, so stroke volume is going to go up. Stroke volume goes up, that means pulse pressure is going up. If the heart is beating stronger, more force, more contraction, it makes sense that systolic blood pressure is going to go up. Diastolic blood pressure is a little bit weird. It might go up a little bit. It might go down a little bit. It might stay the same, because we got to bear in mind blood vessels are dilating in those working muscles. Anyhow, mean blood pressure going to go up. And of course, if stroke volume and heart rate went up, cardiac output are going to go up as well, This is basically what we expect to see. Now then, finally, what we can do is calculate some percent changes. The percent change basically lets me figure out how cardiac output, for example, changed in terms of where it started. So if I've got my cardiac output after exercise minus cardiac output before exercise divided by cardiac output before times 100. So it's basically like we're taking the change in cardiac output and dividing it by the original. So I'm figuring out what fraction of what percentage rather of the original the change was. And we'll times it by 100. And this lets us know how significant the change was. The example I always like to use is if I have a really skinny guy and then a guy who is less skinny, guy, and if they each lost 40 pounds, well, this guy, he started out weighing 400 pounds, right? So if we did the math, 40 over 400 times 100 gives me 10. He lost 10% of his body weight. But this guy over here only weighs 140 pounds. So 140 or 40 over 140 times 100. Well, that's going to be what, like 35%. I just did that in my head, so if I made a mistake, forgive me. But you get the idea. Even though they lost the same amount of weight, 40 pounds, 40 out of 400 was less significant than 40 out of 140. So doing this percent change lets us figure out the significance of the change that occurred. And I can do it for cardiac output, heart rate, stroke volume. I can do it for others too, but these are the three biggies. And all I'm doing here is figuring out the change, dividing the change by the original, and then because it's a percent, I times it by 100. All right, fantastic. That is just about everything. Here is a final list of equations. You need to memorize these equations. They will not be given to you on your test, so make sure you got them. And with that, we're done this lab video. Awesome. I will see you guys next time around. Bye.